So, good evening. Let's start today's session. Today is the sixth week of Fundamentals of Power Electronics. Yeah. Yeah. So, last week we discussed different current limiting circuits for diode bridge rectifier, uh, which uh, which comprised of resistive solution, and thermistor, then transformer, like limiting the inrush current with transformer. And we also saw the op-amp circuit and the contactor and relay circuit, which we usually use for limiting the inrush current. This week, we shall discuss the DC-DC converters. There are two kinds of DC-DC converters. There are linear DC-DC converters, which are also called linear regulators, and there are also switched mode DC-DC converters that we will study later. So this week's topic is linear regulators. Under that comes shunt regulator, series regulator, and some current limiting circuit that we will study. Just think. Mm, yeah. So basically, if we just first we just think the DC-DC linear regulator as a black box, like this part. Just so this part of the circuit we already know. There is this AC supply, then we have the transformer for galvanic isolation, as well as this also helps in limiting the inrush current that we already saw. After that, we have a diode bridge rectifier and a capacitive filter. And in the last class, we saw across the capacitive filter, we have our load, right? Across these two terminals. But here we are adding additional circuit, which is this DC-DC linear regulator. And after this DC-DC linear regulator, we will connect our load here. Our load will be connected here at the output of this DC-DC regulator. Here our load will be connected. So first of all, we need to know what is the requirement of this linear regulator. Why, like we were already getting a DC voltage across this capacitive filter. We were getting after adding this capacitive filter, we were getting more or less a steady DC. So what is the requirement of this DC-DC linear regulator? The requirement is that here, if you see, we can't regulate the output voltage. In the input voltage, when we were solving the numericals, I showed you that the input voltage can vary. There is some range where it can vary. It is not always a constant AC voltage. Like its magnitude can vary and its peak can vary. So if there is a variation in the input side, then there will be some variation in the output also. Suppose you need a very stringent, very strict steady DC value. Suppose you need a 5-volt DC at your output, and in no condition it should vary from 5 volt. But if you only use this circuit, then if there is some disturbance in the input side, yeah, some variation in the input side, that will get reflected here also. This voltage will also vary and you can't regulate it in any way because there is only diode and a capacitive filter. So to regulate that output voltage and to get a very steady DC, regulated DC voltage, you need this linear regulator circuit where you can get a steady DC voltage at a constant value that will not fluctuate with fluctuation in input voltage or any other parameter. It will always be maintained at that particular value due to this linear regulator. That is the requirement of having a DC-DC linear regulator, right? So, and it is a very important circuit in power electronics, but it has one drawback. The drawback is that it is not very efficient. There is a huge amount of loss that is incurred in these linear regulators. That's why for high power applications we use the switched mode converters, not the linear regulators. That we will study later. So its only drawback is that it is very lossy, right? That's why in every application we can't use where we need very highly efficient circuits. There we can't use DC-DC linear regulators. Okay. So the linear regulators can be of two types: shunt regulator and series regulator. First, we shall study the shunt regulator. What is the circuit? This is the circuit. So actually this voltage that we will get across this capacitive filter, this voltage we will denote as Vi. So this denotes the unregulated input voltage. This voltage that we get here, that we will denote as a battery source, and that will indicate the unregulated input voltage, DC input voltage. So this is a DC voltage obviously, but this is a unregulated voltage. So this is Vi. So further in our further discussions, we shall not include this big circuit. Instead of that, this whole thing we will use like this, we will use this symbol to denote this voltage. But actually, this circuit is already always there, and at the output of this circuit, we are getting this Vi. But just for the ease of analysis, we shall just denote it as a battery like this, and this is the Vi voltage. And afterwards, we have this series element, a resistor, and this is the shunt element. So this we call a Zener diode. Okay, this symbol. So you can see this looks like a diode, right? But normal diode we denote like this. Normal PN junction diode we denote like this. But here you have this kind of symbol. So this is called a Zener diode. Okay. And the feature of a Zener diode, how it is different from a normal diode, is that in its operation. So a Zener diode always operates in this third quadrant here. The uh, the static characteristic of a Zener diode is like this. Okay. So for normal diode, we have seen that its static characteristic is like this. There is a knee point voltage or cut-in voltage. After that, the current starts rising. And in the reverse direction, there is very small amount of uh, leakage current, and after that it breaks down. This is the peak inverse voltage. So for our normal diode, we always restrict the voltage below peak inverse voltage. The diode should always block a voltage that should be lesser than the peak inverse voltage. But for Zener diode always operates in the breakdown region. So if you see, this is the breakdown region, right? For normal diode, we shouldn't cross this region. Our voltage should be restricted within this peak inverse voltage. But Zener diode always operates in this region only, in the breakdown region. And irrespective of the current value, like from this point to this point, it will maintain a constant voltage. So at this amount of, this is the current axis, sorry. I think I shall show in the next slide. So if you see this characteristic here, so this is the current. At this point, the current is suppose IZ minimum rated current, and this is IZ max. But throughout this region, the voltage remains constant. The voltage is constant. This is the ideal characteristic, but the voltage is constant, right? So this is the feature of a Zener diode. It can maintain a constant voltage across it irrespective of the current value, right? But here it must be some minimum current should flow through it to enter the breakdown region. Some minimum amount of current should be there, otherwise it will not enter the breakdown region. But from this point to this point, it is maintaining a constant voltage. So that's why for regulatory circuits, for regulating the output voltage, Zener diode is a good option because it can maintain a constant value across it. And we have our load resistor across this Zener diode. So what will be the equations of the circuit? First of all, some input current is getting drawn from the supply. So the input current is flowing like this, and this current is getting divided in two parts. The IZ component is flowing through the Zener diode, and I0 component, this is the load current, that is flowing through this R0, the load resistance. So IN is the summation of IZ and I0, right? So and again IN we can express like this. This is the input voltage Vi minus Vz. Vz is the voltage across the Zener by Rs, this series resistance. In can be expressed in this way also. Okay. So this is a shunt regulator circuit. So like because of the presence of this Zener diode, we are being able to regulate this output voltage. Okay. So no matter whatever, if you change the R, if you change R naught, if there is some disturbance in this out input voltage, some fluctuation, but irrespective of that, the Zener diode can regulate the output voltage at a constant value. Okay. But obviously the current through the Zener diode will fluctuate from this point to this point. But even though the current changes, the voltage is remaining constant at this value. Okay. And we need to define the maximum and minimum current through the Zener diode. So whenever, suppose there is no load current is flowing, these 2 points are open. At that point, we can say the current through the Zener diode will be maximum. And what is that current? That current is Vi minus Vz by Rs. Okay. But then the input current is equal to the Zener current because there is no current flowing through the load. And the minimum current is when the load current is maximum. So Iz plus Io max, that is we are and suppose there is some fluctuation in the input voltage also. So we are writing Vi minimum minus Vz by Rs. Okay. This is the condition when the load current is maximum. So the current through the Zener is very small. And this current should be greater than or equal to this current. This current shouldn't be lesser than the Iz mean current. Otherwise, the Zener will not be in the breakdown region. and it will not be able to regulate the voltage. So these two are the minimum and maximum currents of the Zener diode. Another thing is that we know that there are certain parameters and there are certain limitations when we are using a semiconductor device. For Zener diode, there will be a power rating. So Zener diode, if you see the datasheet of any Zener diode, there will be some power rating. And the IZ max, whatever we require, that should be restricted within PZ by VZ value. So PZ is the power rating that is specified in the data sheet, and VZ is the nominal voltage of the Zener diode. So whatever IZ max you require here, that should always be within this value. Otherwise, the Zener will be damaged. And so here what we need to find, we need to find the value of RS. What should be the value of RS so that we can restrict the IZ max within its rating, and like your IZ mean and IZ max to be the proper values to achieve the values of IZ, like you need to ensure your current through the Zener diode should be in this region, like in this range from IZ mean to IZ max, and IZ max shouldn't exceed this value. So to ensure that, you need to calculate what should be the RS value, and RS also has a range. If you calculate this, you will get a range of RS as well. Okay. So this is the design parameter. This you need to design. RS value should be proper so that you can maintain a proper current through the Zener diode. Okay. Yeah. So we saw this Zener characteristic, but this is the characteristic of an ideal Zener diode. But actually, like a normal diode, Zener diode also has a dynamic resistance. So after this voltage, so the voltage is not exactly constant. It has some slope. It is not exactly a steep characteristic like this. There will be some slope here, and this slope is determined by the dynamic resistance of the Zener diode. So due to this RZ, there is some problem in the voltage regulation. Why? Because now earlier we were seeing this is strictly a constant voltage, but now due to the presence of RZ, this voltage can fluctuate based on the current. If this current is very high, then there will be some drop, IZ-RZ drop across this dynamic resistance. And then your voltage will no longer be constant, it will vary. It will vary from this value, right? Because there is some drop through across this resistance. So we have to see how we can minimize this fluctuation due to the dynamic resistance of the Zener diode. This occurs due to the non-ideality of the Zener. Like all the other devices, Zener diode also has some non-ideality, and due to that there is some problem in voltage regulation. Okay. So we have to come up with some modified circuit where this fluctuation will not affect the voltage regulation. This is the modified circuit of a shunt regulator. So what are the additional components that we added? So first of all, you can see that we have added a BJT here, right? We have added a BJT here, and otherwise the circuit components are same, and the base of the BJT is connected to this node. Earlier we were connecting this node to the output node, but now the base of the BJT is connected here. And how this improves our performance, how this improves the performance of the circuit, because now the base of the BJT is connected here, so the IZ fluctuation will be dependent on this base current of this BJT, not the entire load current. Obviously, load current value will be much higher than the base value of this BJT, base current value of the BJT. So now we have connected the base of the BJT here. That's why this IZRZ value becomes very small. The fluctuation is very small because now IZ is dictated by this base current and the base current is very small. That's why IZRZ will also be very small. Now, what is our output voltage? Our output voltage is VZ. This is the VZ value plus IZRZ and minus VBE, because there is a drop VBE in this base emitter junction of the BJT. So in this loop, if you apply KVL, you will get the expression of output voltage, right? So now what happens is that this is, if this is our I in is getting divided between this Zener and this base of the BJT, right? Now, and if you are giving some base drive to the BJT, the BJT will turn on and then load current will flow through the load, right? Because the BJT will be on and some load current will flow through this BJT to the load. And the base current, if this is our if this is the load current and the load current is equal to the emitter current of the BJT, so the base current is I naught by beta plus 1. We already studied beta, right? This is the current gain of this BJT. We also denote it as HFE. So if I naught is the emitter current, the base current is I naught by beta plus 1. So now this current is much smaller than I naught, right? So this IZRZ drop, this drop becomes much lower than our earlier case where the IZRZ drop was, this IZ was dictated by I naught. So that value was much higher than this case because now IZ is comparable to this value, to this base current. That's why this drop is much lower than the earlier case, and now we can have a better voltage regulation. Okay. So if you don't understand, just tell me. Okay. I am proceeding to the next part. If you don't understand, just ask me that and ask me which part you didn't understand. So there are various applications of shunt regulator. The first one is to have voltage reference, a reference voltage that we already studied, that there will be some supply voltage, after that there will be a series resistance, there is a Zener diode, and across this we have a resistance. But now instead of a constant resistance, we have a pot. We have a potentiometer. Okay. So if you just tap it across this, you can get different output voltages instead of a single output voltage. So the Zener diode will maintain a constant voltage across it, but as you have connected a pot across it, so instead of this position of the tapping, you can get a variable voltage here, and you can get a you can get a reference voltage from this potentiometer. Okay, this is a this is an application of shunt regulator. What are the other applications? The other application can be a current regulator. Okay, earlier we saw a voltage regulator where we can get a constant output voltage. Here we can get a constant current through the load. How we can get it? So first see the circuit carefully. Here we have a VCC, our supply voltage. Then we have a Zener diode. and we have a series resistance here. Okay, this is one path. Another path is there is another resistance, and then with that we have a BJT, and then we have a load resistance, and the base is connected like this. So now how it regulates the current, the load current. So if you see here, the emitter, this is a PNP resistor. Okay, this is a PNP resistor. You can see from the arrow here. So basically here, what is the emitter current of this BJT? The emitter current we can find out very easily. So we have this VCC here. Okay. This is the supply voltage. This is a constant value. And the Zener diode is suppose is maintaining a voltage Vz across it. Okay. Suppose this is a constant voltage Vz that the Zener diode is maintaining across it. So if you apply KVL in this loop, so Vz, so IERE drop, the drop across this resistance will be what? Vz minus VBE, but here we shouldn't say actually VBE because this is a PNP resistor. Uh, we can write here. So basically this should be VEB actually. VEB. Because the drop is from emitter to base. This will be plus, this will be minus. The sign will be like this. This is plus and this is minus. And here this is the Zener diode voltage Vz. So Vz minus VEB, that will be the drop across this resistor, and if we divide the resistor value, we can get the emitter current, IE, right? That will be our emitter current. If we have the emitter current, we can easily find out the collector current. And collector current is nothing but the load current. So this is the collector current, and this current is flowing through the load resistance R naught. So I naught is what? Emitter current minus base current, right? Because emitter current is always the summation of base current and collector current. So, and we know if our current gain is beta, if the current gain of this BJT is beta, so IB will be I naught by beta. So if you just solve this, you can get this expression for I naught. IE into beta by beta plus 1. Okay. So if you see IE is not dependent, so VZ is constant. VEB, this value is more or less constant. That this is the forward voltage drop. So this is also a constant value. This obviously changes with temperature, but right now we are not considering that. So these two values are constant and RE is also constant. So independent of this R naught value, IE is constant and beta is also constant. So this load current is constant here. You see there is no like VCC or R naught. There is no expression. In this expression, you can't find R naught or VCC. So irrespective of this load resistance value, it will maintain a current which is a constant value. Okay. So you can have any value of resistance, but it will maintain the same current, right? So that's how this current regulator works. So is this fine? Okay. Uh, So this is the current regulator. Okay, we shall go to the next. So another regulator is a series regulator. Earlier we were talking about shunt regulator because there the Zener diode was connected across the load. That's why it was a shunt regulator. But now we will talk about series regulator. And series regulator is much more popular than shunt regulator. You will see this is used uh, this is where like used much more than the shunt regulator. This is very popular in industries also. Okay. So yeah. So let's understand how this series regulator works. Here we have this again, we have this unregulated DC input voltage, and here again we have a series resistance. Okay. But this is a variable resistance. This is not a constant resistance. Okay. And then we have a load resistance here as well. But here you can see there is no shunt, there is no Zener diode or anything. Here only we have the series components. That's why it is called a series regulator. And the working principle is, suppose you want to maintain a constant voltage here, okay, irrespective of the fluctuation in the input side. So what you will do is there will be one controller. So here you will tap the output voltage and you will give a feedback. This is a feedback, okay. So this is minus and there will be one reference voltage, that is plus. And the difference of this reference and output, that is called the error. So this is the error. What the circuit will essentially do is, suppose you want a certain amount of voltage at the output, but due to some disturbance in the input side or some other cause, the output voltage starts rising. It rises from the required value. It increases. So what will happen is, as we are giving feedback here, so VO reference is constant. This is a constant value, that but this value has increased. So obviously the error will increase. The error is the difference of VO reference and this output voltage. So if this is a constant value and if your VO value increases, so the error will decrease, right? The error will decrease. If the error decreases, then what it will do is, it will increase this resistance value. Okay. If it increases the resistance value, then there will be more drop across this resistance, right? So if there is more drop across this resistance, the output voltage will decrease. And again, it will go back to its original value, the required the desired output value. Okay. So that's how this controller works. If V naught decreases, then this error increases, and if the error increases, it decreases this resistance value. Then the drop here decreases and the output voltage increases. Okay, because here V in is what? Vi is the summation of Vi is here is the summation of. Suppose this voltage we can suppose we call this a voltage uh, VRS, okay, VRS. So VI is the summation of VRS and V out. So suppose your V naught has increased. So if you increase this voltage, then again VO will come down. And similarly, if V naught comes down from the actual value, then you will decrease this value so that V naught again increases to its original value. Okay, that's what the controller does. Now we have modeled it as a variable resistor, but actually we use a BJT circuit here. Okay, so the BJT circuit is basically we have modeled by this variable resistor, but the actual circuit is like this. So here we have one BJT Q1 and we have the load resistor, and with the base of this Q1 we have connected another BJT. Okay, and here we have a Zener. So this is again a shunt regulator, But that regulator basically just gives us the reference voltage that we already saw, right? That one of the application of shunt regulator is giving a reference voltage. So that's what this Zener diode does, giving the reference voltage. And here what we are doing in this part, we are tapping the output voltage, and here there is a resistive divider. So we are attenuating the output voltage and we are giving feedback. So this, we were getting feedback here, right? So this is the feedback. First we are attenuating the output voltage because it may be that the BJT can't take this much high value. So that's why first we are attenuating this output voltage and we are giving the base drive to this Q2. Okay, via this point. And if you see here, there is a base drive resistance here, RB. And from this point, there are two current paths. One is going to the base of Q1 and another is coming to this path through the collector of Q2. Okay. So let's see what happens. So uh, suppose we have a constant, we have a constant reference here. And suppose we had our output voltage has increased from its previous value. That we don't want. We want to maintain it at a constant value, but somehow it has increased. Okay. So what will happen if V naught increases? Suppose if V naught increases from its actual value, then this A V naught will also increase because these values are constant. So if V naught increases, A V naught also increases. A V naught also increases. A V naught is a voltage that is providing the base current to this Q2. So if A V naught increases, then the base current of Q2 increases, IB2 increases, right? IB2 increases. If IB2 increases, then obviously the collector current through the Q2 will also increase, right? Beta times, because as I beta increases, I collector will also increase. So this current increases, that is that Q2 is drawing. I collector also increases. I collector increases. Okay. As it starts to draw more and more current, so but this current is more or less constant, right? The current through the RB. Why? Because here you are getting this input voltage, right? Here you are getting this input voltage. So, and here suppose we have some drop. So this current is more or less constant, but it is starting to draw more current. So the base drive through this BJT will decrease, right? Because this is drawing more current, so the current through this base will decrease. If the base current of Q1 decreases, then what will happen? It will start to go towards the cutoff region, right? Because base current has decreased now, so it will start to go towards the cutoff region and it will start to block more and more voltage. So VC1 will increase. VC1 will increase. And if VC1 increases, then output voltage will again come down. So output voltage will come down. So you see how this works. First, the voltage increased, output voltage increased. As the output voltage increased, the feedback went here. So this is the feedback. So the feedback came here and then it caused the base current of this Q2 to increase. As this base current increased, the base current through Q2 decreased, right? Then as the base current of Q1 decreases, the voltage drop VC1 of Q1 increases. And as this drop increases, then output voltage will decrease, because out the input voltage is the summation of this voltage and this voltage. So if this increases, this has to decrease. That's how it regulates the output voltage. Okay, that's how it regulates. Okay. So if we see the efficiency of the series regulator, so efficiency is nothing but P output by P input, the output power divided by the input power. So here if you see, the current flowing through this element is the same current that is flowing through this element. Okay. So here your current is same, right? The current that is getting drawn from the source, this current, that is the input current, and the current that is coming here, this is the same current because all are in series. So that's why the efficiency is nothing but the ratio of output voltage and input voltage. So if the difference of output voltage and input voltage, this delta V, this is called the differentiator of output voltage and input voltage. Suppose Vi minus Ve, Vi minus V naught, right? So if this difference is too high, then your efficiency will be less. And if Vi and Vo, they are very close, their values are almost equal, very close, then your efficiency will be high. Okay. Okay. Next we have the current limiting circuits. So till this point, do you have any doubt? Okay. So now, now we shall discuss the current limiting circuit. Okay. So here, this portion is same, right? This portion is same as the current regulator circuit. This RB, RZ, this Zener diode, this Q1, Q2, these portions are same. You can see these portions are same. The only difference is what? We have added another BJT here. We have added another BJT Q3 here. The base is connected from this point, and we have connected one series resistor here, RS. Okay. So this is the additional components that we have connected for to implement the current limiting circuit. Now, how does this work? So suppose your this is your I rated output current, I0 rated. Okay. Your rated output current. If you see in this loop, okay, so this is the emitter, this is the base. So base and emitter. If you see this, so this I naught is flowing here. What is your VBE? VBE is I naught RS. I naught RS. Right. You just see this loop. In this loop, this is your VBE drop, and this is nothing but equal to the drop across this resistance I naught RS. Okay. So suppose your I naught is lesser than the uh, so if at some point your I naught is lesser, I naught RS drop is lesser than this cut-in voltage, then uh, and so at this point what is the voltage? So if you see this loop, okay. So in this loop, if your VB is equal to I naught RS, then there is some base current that will flow here. And if some base current flows here, so some current will flow here also. It will draw some current from this point, right? And if it draws some current from here, so now you see this current is getting divided to this BJT, and to this BJT. Okay. So now the base current through this Q1 further decreases, right? So this enters the cutoff region, and then it blocks a very high amount of voltage, and this voltage becomes very smaller. Okay. So then I naught also becomes lesser. Okay. That is the working principle of this current limiting circuit. So by adding this BJT, we are ensuring that the drop across this the voltage blocking, the blocked voltage here it increases. As this voltage increases, then like we said earlier that the output voltage will decrease and the current through it also decreases. Okay. So this is kind of the characteristic. Suppose this was so this was your, suppose your V naught, and this is your I naught here. This is your I naught. Sorry. Yes. So till this point, this is suppose I naught rated. This is the rated current. Okay. And if at this point, if you short this, there is no resistance, then the voltage will immediately become zero. Okay. But the current will be very high. That we call the short circuit current. This is called ISC. Okay. So in this condition, to restrict this short circuit current, when there is the resistance is shorted, we use this circuit to limit the current. Okay. Okay. So now let's take a 5-minute break. Then we shall again resume the discussion. Okay. So now the time is 6:55. We will again resume at 7. Okay. So let's assume our discussion. Okay. Yeah. So we were discussing. You can see the screen, right? Yeah. So we were discussing this current limiting circuit. Okay. So here you need to design the RS in a way so that this current is your rated current and VBE drop, this is a constant drop 0.7, so that when it reaches the rated current and somehow if even if you short this resistance, so it can restrict the uh, it can uh, it can restrict the current, or it can make this Q1 to go to completely in cutoff region so that it blocks the entire input voltage and there is no voltage that comes here, so the current becomes zero. Okay. We have another circuit, current limiting circuit, that we call fold back current limiting circuit. So if you see now here, the circuit is a little different from the previous one. Here there is a BJT and there is a voltage divider circuit. Okay. So the voltage at this point is what? I naught RS plus V naught, right? At this point with respect to ground. And the voltage at this point is what? V naught. Because this is the V naught voltage, output voltage. So at this point, the potential of this point with respect to ground is V naught. The potential of this point with respect to ground is I naught RS plus V naught. Because there is a resistor and there is some drop I naught RS across this resistor in this way. So what essentially happens is that there will be some base current that will be flowing here. What will be the base current? The base current will be, so this is VBE3, this is the drop, right? So the drop will be, VBE3 will be what? VBE3 will be alpha times I naught RS, I naught RS plus V naught, because we are attenuating the voltage at this point. This voltage we are tapping here. And but here again you are giving feedback of this voltage. This is V naught voltage. That is again coming here. So you need to subtract the voltage V naught here, right? Because here the potential of this point is V naught with respect to ground. Okay. So VB3 will be this expression where alpha is what? Alpha is RB by RA plus RB. This ratio we are calling as alpha. Okay. So this is our VBE3. So you will have to design the RS value so that at this is designed at rated current. This current will be at rated condition. Okay, this is the rated current. So suppose now what happens is this is short. There is no load resistance. So then there will be the short circuit current ISC, right? So in that case, your VO becomes zero because this is short. There is no voltage here. So VO becomes zero. Then what is your ISC? ISC becomes I short circuit basically. I short circuit is So V naught is 0. VBE3 by alpha RS, right? This is your short circuit current. Now, if you see your output current expression, again we can use this equation. And if you rearrange the equation, what will be, this is in normal condition, okay? There is no short circuit. So in normal condition, what is your output current? Your output current expression is this is alpha, right? So it becomes VBE3 by alpha RS, and there will be additional term which comes due to the presence of V naught. So this is, it is V naught and this is alpha V naught, right? So this becomes 1 minus alpha V naught by again alpha RS, right? So if you see, this portion is the short circuit current, right? That we already saw. This is the short circuit current. So uh, the advantage of this circuit is, so if you see, I shall take another slide. Okay. Slide. So the beauty of this circuit is that here, if suppose at your rated condition, so suppose this is your V naught, this is your I naught. So again, like previously we saw that your V naught was constant, and at this point, suppose this is your I naught rated. Okay, this is suppose I naught rated. And if the short circuit happens at this point, then the current will decrease from this value, and suppose this is your short circuit current. That's why it is called a fold back circuit. Why? Because the current is coming here, then if there is some short circuit, the current is reducing, right? Why? Why? Because we already saw, right, mathematically, that your I naught is the summation of ISC plus some portion. In short circuit condition, the V naught is 0 because you are shorting this. So this term vanishes. This is the short circuit current. So if you design it for your rated current condition, then if in the occurrence of a short circuit, the current will come down from this value to this value, which is your short circuit current, right? So that's why it is called a fold back current limiting circuit. So these are more or less the summary of this week's content. Now we shall start the problem solving part. Okay. Before that, if anybody has any question, you can ask. Okay. Let's see the first question. The current limiting circuit is given below. Calculate the RS resistance in milliohms so that the rated load current can be limited to 10 ampere. Assume all the transistors have same characteristics, that is, all the transistors have VB drop of 0.7 volt. So this is the first current limiting circuit that we saw, right? We saw two types of current limiting circuit. The first one, constant current limiting circuit, then the fold back current limiting circuit. So here I already told that you need to design this RS value in a way so that the at rated condition, when the rated output current is flowing, the drop across this RS resistance I naught RS, that is equal to 0.7 volt. Okay, the VBE drop, so that it can turn on and it can draw some current from here. Then only the base drive to this device will be very small and it will almost go to cutoff region, right? That's why the drop across this RS resistance should be at least equal to 0.7 volt. Okay, so there is no, like, the calculation is very simple. The RS value will be simply what? 0.7, that is the VBE drop, 0.7 by the rated current. So they have asked to limit the rated current at 10 ampere. That's why 0.7 by 10, that gives us 70 milliohm. That is the required resistance here, right? So the idea is your drop is at rated condition, the drop is equal to the VBE drop here. So that's how it goes into the cut-in mode and it starts drawing current from here. As it starts drawing current, the base current here reduces and this transistor goes near cutoff region. Okay, and then there is a very high voltage blocking across this transistor, and here the current reduces. Okay, because V naught reduces. Let's see the next question. So the given series regulator has the following parameters. So they have given the input voltage, the load resistance value, the Zener voltage value here, and all these resistor values. The parameters of Q1 are given. The parameters for Q2 are given. So, what they have asked for the series regulator, what is the value of X? X is what? X is defined as this attenuation ratio, R2 by R1 plus R2. So this value you need to calculate. Okay. So how will we calculate? So, can anybody give any clue, like how should we proceed here? Okay. So, see here, actually here, very a lot of data is given, but actually you don't need this many data. This is very simple problem. What you need to do is, first you need to calculate the output voltage. What will be the output voltage? So V in is already given. V in value is given in the problem. And what else is given? VCE1. So the drop across this transistor Q1, VCE1, the drop is given. Okay. So if you know this voltage and this voltage, you can calculate the output voltage. That's what we have done. V in minus VC1, that gives us the output voltage, the voltage across the load resistor. So if you have the output voltage, then there is nothing. You just, and what is this Vx value? This Vx value, if you follow this loop, Vx value is Vz plus VBE2, right? So this is your base emitter voltage and this is your Zener voltage. Vx is basically the summation of VBE2 and Vz. Okay. And what is Vx? Vx is the attenuated output voltage. So attenuated output voltage means x V naught, that is equal to 3. And you know V naught is 15 volt, so x comes out to be 0.2. Okay. So the first step was to calculate the output voltage. This drop was given to us. So this is VCE1 drop. This drop was given in the problem. Okay. And if you follow this bigger loop, so this bigger loop, starting from this to this, if you apply KVL, then V in equal to what? VCE1 plus V naught, right? VCE1 plus output voltage V naught. So if you know this and this, V in is given and VC1 is given, we calculated V naught, and from V naught we can follow these steps to calculate the value of X. So Vx is the attenuated voltage. Vx is nothing but the voltage that we get across this resistor R2. And X is given R2 by R1 plus R2. Okay. So that value is 0.2. Okay. What is the next question? What is the efficiency of the current regulator circuit below? So this is a current regulator circuit. They have asked the efficiency. So for efficiency, what we need? We need the input power Pi. We need the output power P out, PO. Okay. And if we know these two quantities, we can find efficiency. So P out will be the power absorbed by this load. This is the load resistance, R load. So the power absorbed by this load, that will be our output power, and input power will be whatever is the current, that is so the multiplication of the source voltage 15 volt multiplied by the source current that is drawn from the source. Okay, I input. So if we can calculate I input, then multiplying it with the source voltage, we can get the input power. So let's see how to do that. So here they have specified a particular Zener diode. So if you see the data sheet of this Zener diode, you will see the Zener diode voltage is 9.1 volt. This is the Zener voltage rating. So now we can calculate the emitter current of this BJT, this current. So this current that is going towards the emitter. What is this current? This Vz minus VEB. So this is a PNP resistor. So this is the VEB drop. This is IE, the emitter current. This is IE. This is IE. And the base current flows like this in this direction. IB. And here the collector current flows. Okay. Collector current flows through the load resistance. So I is what? This is our VZ, right? So you will have to simply apply KVL in this loop, in this upper loop, in this loop. So VZ minus VEB by this resistance. This is RE. Okay, this is RE. So we can find out emitter current. The beta for this resistor is given 85. So we can easily find out what is the load current. Okay, so load current is 0.825 ampere. And what will be the base current? Base current is I naught by beta. As your load current and collector current, they are the same. So if you divide the collector current by beta, you can get the base current. This is the base current. So you have this, they have already provided, this is our output voltage 4 volt, and we have already calculated output current. So output power is V naught I naught multiplication of output voltage and current. So this is 3.3 watt. We have already calculated now the output voltage. Now we need to calculate the input power. Okay. Output power we have calculated. So now what is the current through the Zener diode? The current through the Zener diode is, if this is the current through the Zener diode IZ, so here some base current is coming, and this current is basically the sum of the Zener current and this base current. Okay. So that's why what is this current? This current is, so there is a 9.1 volt drop across the Zener. So the current through this resistor is what? 15 minus 9.1, the Zener voltage, by 300, right? And minus IB. We have to subtract this base current. So this comes out to be this 0.00996 ampere. And what is our supply current or input current? Input current is basically the sum of the Zener current and the emitter current, right? The supply input current is getting divided in two parts. Some portion is flowing as the emitter current and some portion is flowing through the Zener. So this is, I have written IE plus IZ. IE we already calculated. We already calculated IE, and IZ is this current. The summation is this. Now we also have the input power. So the efficiency is output power by input power, which is 26%. See here, so I already earlier I told you the efficiency of the linear regulator is very poor. So you see the efficiency here is only 26%. Right. So here the efficiency is very low. That's why we can't use the linear regulators everywhere due to the poor efficiency. Okay, let's go to the next question. What they are asking, if the input voltage ranges from 20 volt to 30 volt and the Zener breakdown voltage is 5 volt and the dynamic resistance is 2 ohm, find the minimum value of output voltage as indicated in the circuit. So they have given the Zener voltage and also the dynamic resistance value. So they are asking us to use the non-ideal model of the Zener. So this is not ideal Zener because here they have provided the dynamic resistance along with the Zener voltage. Okay. So basically, just if this is the Zener, the actual model of the Zener is some resistance along with a constant voltage. So this is Vz and this is Rz. Rz. So Rz value is 2 ohm and Vz is 5 volt. And the range of input voltage is given. As they have asked for minimum value of output voltage, we will take this voltage 20 volt because we need to find the minimum output voltage. So that's what I have written. The lower limit of output voltage, input voltage is taken to find out the minimum value of output voltage. So here I have taken two loops. This is the first loop, okay? Suppose this is the input current I in. This is the input current I in, okay? So I in have two parts, IZ, IZ and I naught, the load current, right? So here in this loop, this is suppose loop 1. In the first loop, this is in for loop 1. In the first loop, we can write, so 200 I in plus RZ IZ, right? Because there will be a resistance, dynamic resistance, RZ IZ, that is this supply voltage minus this Zener voltage, right? There will be, this is basically this one, right? You imagine like one resistance and one constant voltage which has a value of 5 volt. So after applying KVL, we get this equation. What is the second equation? The second equation is in this loop. In this loop. So our output voltage is what? Vz plus Rz Iz, okay? And that is equal to I naught R naught. So this is R naught. R naught value is given 1 kilo ohm and I naught R naught, okay? And your input, that I already told, your input current is nothing but the sum of Iz and I naught. So I in you can replace by Iz plus I naught. Iz plus I naught, okay? So then you have two unknowns, Iz and I naught, and you have two equations. If you solve these two equations, you will find out Iz value and I naught value. And if you have found out I naught value, what is your output voltage? I naught times R naught. R naught is already given and I naught you have calculated. So the multiplication of I naught and R naught gives us the output voltage, and this is the minimum output voltage. Why? Because we have found out the output voltage corresponding to the minimum value of the input voltage, which was 20 volt. If we have considered the highest limit, that is 30 volt, then we would get a higher value of output voltage, right? So this value is the minimum value of output voltage. Okay, let's go to the next problem. So here some parameters are given. Choose the linear regulator from the table that satisfies the following specifications. So input voltage range is given 16 to 24 volt. DC output voltage adjustable range, that is 8 to 12 volt. Recommended inherent current handling capability is 4 ampere. So this is the current handling capability of the linear regulator. And these are the stability parameters: temperature coefficient, line regulation, load regulation. So here let me just tell you, there are certain parameters, performance parameters, that we define for a linear regulator. Okay. Sorry. There are certain performance parameters. Among them, there are linear regulation, load regulation, and temperature regulation. Okay. You can refer to Umanand sir's lecture for having more details about the regulations. But these are the performance parameters. So line regulation is basically your delta V naught by delta V del Vi times Vi. Okay. Similarly, there is load regulation, that will be del V naught by del Vi times del V naught. Okay. And we have also temperature coefficient. You see sir's lecture. So there you will get one lecture where the performance parameters are given. Okay. So in the question, they have given a table where multiple linear regulator, the parameters of multiple linear regulators are given, and from them, among them, you need to choose the regulator which will be appropriate, so that you can abide by all these specifications, where your temperature coefficient is less than 2%, line regulation is less than or equal to 0.5%, load regulation is less than or equal to 0.5%, and it should be able to handle at least 4 ampere continuous current. Okay. So let's see. So there is no calculation as such. Here the I out max is given 5. This is 5 ampere. This we cannot use because it is 1.5, but we need at least 4 ampere. So this can't be used. So these three are 5 amperes. Okay. Now line regulation. So line regulation, this is already crossed. So we will not see this one. So this one is 0.04. This is 0.2, 0.2. So this is the minimum. What is load regulation? So load regulation value should be less than 0.5%. So here it is 0.6%. So again, this is cancelled. So this one is okay, and this one is okay. Okay. Temperature stability. So 0.5 and 0.5. And this one is also okay. 0.5 and 0.5 both are. Input output differential voltage max. What is this parameter? Input output. So this parameter is basically Vi max minus Vo min. Vo min. If you see in the problem, there is some range that is given for input voltage, some range is given for output voltage, right? So 8 to 12, and this is 16 to 24. So the maximum input voltage is 24 and the minimum output voltage is 8, right? So uh, what is the desired input output differential voltage? That is our required is 24 minus 8, right? That is 16. That is required for our to abide by our specification. But here, if you see the last one, its maximum recommended input output differential is 13 volt, which is less than 16. So again, this can't be used. So this is the only one that we can use, which maintains all the conditions, right? So the third one we can use for this specification. Let's see the next question. In the figure below, a snippet of the typical application circuit of LM317 IC is shown from the datasheet. Using this circuit, find the value of the variable resistor R2 in kilo ohms to obtain output voltage of 10 volt. So if you need to obtain an output voltage of 10 volt here, what should be your R2 value? this resistance value. What should be the value of R2? So if you see here, this voltage is given. This is the reference voltage. It is given. This is the constant value. It is 1.25 volt, right? So here this calculation is also very simple. Like just seeing the problem, it may seem it is very complicated, but this is a very simple problem. So we know the voltage across R1. This is 1.25 volt, right? And this is a resistive. And in the question, they have also said that assume I adjust equal to 0. So this current, the current in this branch, they have said you can assume it to be 0, right? If the current through this branch is 0, so this is a resistive divider circuit simply, right? This potential is V naught. This potential is V naught with respect to ground. And this is a resistive divider circuit where R1 and R2 are connected like this. So if you see, we know this voltage and this voltage is across this resistance R1. So V naught into R1 by R1 plus R2 is 1.25, right? Because we know this is 1.25 and this is across R1. And if you just rearrange it, so we can get 1 plus R2 by R1 is 10 by 1.25. So we already know R1 value is 240 ohm. If you calculate, R2 value comes out to be 1.68 kilo ohm. Okay. So this is a very simple problem. What is the next question? Based on the information provided in question 8, find the maximum value of thermal resistance from junction to ambient in degrees Celsius per watt for load current IO equal to 1 ampere, input current 1.5 ampere, input voltage 15 ampere, and R2 by R1 ratio is 3. Okay. And ambient temperature is 25 degrees Celsius, junction temperature is 100 degrees Celsius. What you need to find? You need to find the maximum value of thermal resistance so that you can restrict the junction temperature maximum at 100 degrees Celsius. Okay. So again, this is very simple. Earlier we studied that how to calculate the thermal resistances, right? So this is the formula Tj minus T ambient by the power loss. This is the P, this P is the power loss. Okay. So they have provided the input current and input voltage. You can get what is the input power, that is VIII 22.5 watt. Output voltage we can calculate because this voltage is again 1.25 volt and they have given the ratio R2 by R1 as 3. So like we calculated in the earlier question, here we can find out output voltage, right? Which is 1 plus R2 by R1. So this comes out to be 5 volt. And they have given the output current, output, this is output power. This is output power. The output power is 5 watt. And so you can calculate the loss, which is the difference of input power and output power. And from there, you can calculate the thermal resistance from junction to ambient, which is 4.285 degrees Celsius per watt. This is the maximum thermal resistance. It should be less than or equal to this, not more than this, so that you can restrict your junction temperature at 100 degrees Celsius. Okay. Let's see the next question. The next question is, which of the following statements is valid for the foldback current limiting circuit? So first option is short circuit current limit can be set lower than the rated load current. Second option is short circuit current limit can be set higher than the rated load current. short circuit current limit cannot be altered using fold back current limiting circuit. And last option is short circuit current limit is the same as the rated load current. So we already saw the circuit operation, right? So what was the characteristic? The characteristic was something like this. So first this and then this, and this was our rated current. This was our rated current. Okay. This is our I naught rated. I naught rated. And this is short circuit current. That's why it is named fold back, right? Because you can design it in a way so that your short circuit current limit is lesser than the rated current. So the correct option is option A. Short circuit current limit can be set lower than the rated load current. Okay. So this is the last question. So do you have any question regarding the circuit operation or the numericals that we solved today? So I shall suggest that you attend the lectures, okay? If you attend Umanand sir's lecture, then you will understand better because I could not discuss all the concepts very elaborately. So if you don't understand any concept, you go through the lectures. And if you have any other doubt, you can ask me in the next lecture, in the starting of the next live session. There I will answer if there is any doubt. Okay. So if you don't have any question, I shall end today's session.